Good afternoon, I'm Tim Sever, and today in our Introduction to Programming in Python, in this video we will determine whether an integer is divisible by 2 or 3, but not both. Along the way, we're going to consider 5 cardinal examples as we work through this problem. The coding of example 1 is in essence the AND versus the exclusive OR condition. In example 2, we have an initial exploration into the 4 distinct cases. Example 3 will be a rework of example 2, fleshing out the code in a slightly redundant way. In example 4, we will rework the logic, considering in the OR case first, and then we will begin a general exploration into the 2-variable Boolean case, terminating with the code for example 5. I hope you enjoy this video. Let's get going. Today, in our Introduction to Programming in Python, we're going to look at this particular programming problem. We're going to determine whether an integer entered by the user is divisible by 2 or 3, but not both. For this video, we will run our sample programs on the following test data. 306, which we see is divisible by both 2 and 3. 154, which is divisible by 2 but not 3, 195, which is divisible by 3 and not 2, and then 385, which is divisible by neither 2 nor 3. So, and I'm showing the factorization here so that we can ascertain the veracity of our sample code results. So let's look at the first simple coding example. So here's our code sample. I suggest that you pause and peruse the program in a little more depth, and I'll go through the basic statements individually. So here we see we're inputting a number from the keyboard. Now we know that there could be some issues with this input, and we're not testing the true veracity of the user input at this time. So we're assuming that the input is going to be entered correctly. We know that there will be some issues where there will cause some runtime errors if we don't enter an actual number. So we're going to print a blank line. So we have two Boolean variables, div by 2, div by 3, which stand for is num divisible by 2 and is num divisible by 3 respectively. So you can see we're inspecting the remainder. Here when you divide by 2, that's num modulo 2, and we're testing the condition, is that equal to 0? Similarly, we're testing the condition, is num mod 3 equal to 0? So in each case, if the Boolean variable is true, it means the number is divisible by that factor. So let's look at the logic. So here we have the Boolean variable div by 2 and div by 3, which really means if div by 2 is true and div by 3 is true, then we enter this code block, the first code block. And that means that we're going to print out, and here we have a formatted string, an F string. The number you entered, num equal num, is divisible by 2 and 3. Okay, else if the number is divisible by 2 or it's divisible by 3, and then we'll print out the number you entered, the num equal whatever the number is entered, is divisible by 2 or 3, but not both. Now remember, this condition's already been tested. So we know that if we get into this code block, num cannot be divisible by both 2 and 3. And in this case, the third case, what happens in the else? Well, this condition didn't hold, nor this condition was true. So it must be the case that if we look at the logic here, then the num is not divisible by 2, and it's also not divisible by 3. And then we print out the appropriate statement accordingly. So let's look at the code, the result of running this code. Okay, so we're running example 1. Let's enter our test data. 126 was our first number. And as we see, it's divisible by both 2 and 3. Let's run the example 1 on our second number, test number 134. It's divisible by 2 or 3, but not both. Finally, 195. Once again, it's divisible by 2 or 3, but not both. And finally, 319. And it's divisible by neither 2 or 3. which is what we agreed to in the beginning. Now, the problem with this code, it doesn't break it down. It doesn't tell you, for example, in the case of 154, it just says it's divisible by one of them. It doesn't actually say that it's divisible by 2 and not 3. Similarly, for 195, it does not tell us it's divisible by 3, and it's also not divisible by 2. So this program is very coarse, program example 1. It just answers at the highest level whether the OR condition holds and the AND condition holds. So whether it's divisible by both or divisible by one of them. When you construct the code in this sequence, when you're in this block here, you're now looking at what we call the exclusive OR case, because we've ruled out the case that they're both true. So this program does not give us the results that we would want. Namely, it does not tell us that it's specifically divisible by 2 but not 3, and in the next case, or in the other case, it's divisible by 3 but not 2. So it's good, but it's too general. It doesn't go through all the possible states of being. So let's look at a refinement of this example. Let's look at example 2. We have the same beginning to the code. We have our same Boolean variables. Now we look at our if-elif-else ladder. Let's see what the logic is here. So again, we check the AND condition first. If it's divisible by 2 and divisible by 3, then we, of course, print the appropriate statement. Now, so else, then we look if it's divisible by 2. Now what this means is we already checked that it was not divisible by both. In terms of our coding logic, once we enter this block, namely this div by 2 is true, what do we know logically? Well, we know it's divisible by 2, but not 3, because it can't be divisible by both. Otherwise, it would not have made it into here. And that's, of course, what we print out. Else, it's divisible by 3. Again, if it enters this code block, we see that it's divisible by 3, but not divisible by 2, because, of course, we've already tested the case that whether it's divisible by both. So in both of these cases, we're implicitly saying it's not divisible by 3. In fact, that's really the basis of our next example. We'll actually flesh that out explicitly. And then we look at the final case, else, when we go through the logic. So let's see. It's not divisible by both. It's not divisible by 2. And it's also not divisible by 3. Well, that leaves us one and only one case. It has to be divisible by neither 2 nor 3. And let's look at this code example. Okay, so here you can see we're running example 2. Let's enter our same sample data, 126 first. It tells us it is divisible by both 2 and 3. There's not much more we can say about that case. That is fully correct. Let's look at 154. And now we see we have more information than we did in example 1. We are clearly seeing it's divisible by 2, but not divisible by 3. Looking at 195, our third datum, we have entered the number 195, and it is divisible by 3, not divisible by 2. Again, this is an improvement over example 1. And our last number of 319 is, again, divisible by neither. So that's pretty good. That's exactly what we wanted. Moving on to another third example. This is really example 2, where we have this condition being written explicitly. If you compare to example 2, and if you were thinking in a Pythonic way, you would say that this AND is redundant. You don't need to check this, and this is correct. You don't really need to write this. Let's quickly go back to example 2, and you'll see the difference between example 2 and example 3. We have an extra AND condition. This is the redundant AND condition. So this is redundant, but when you look at this from an introductory perspective, it may be a little easier to read the code and for the beginning programmer to see the logic here. While it's certainly redundant, that's the basis of example 2, these two, at least we can see the exact condition being tested. We know that this condition is absolutely true due to what was tested here. But nonetheless, this is basically a slight variation of example 2. technically written a little redundantly, but it's a little more explicit as to what comprises these four cases. So we have here divisible by 2 and not divisible by 3. The next case in our ladder is divisible by 3 and not divisible by 2. And I think then when you look at this else down here, it's a little more clear that this one, in the first case, is divisible by both. In this case, it's divisible by 2 but not 3. In this code block, we see it's divisible by 3 but not 2. So what's left? It's not divisible by 3 and not divisible by 2. So this one is really the exact same as program 2 or example 2, except it's a little redundant. We've written out the implicit state here. We've written it out explicitly. So in this way, it's no better, and for some, we might say it's a little worse. And if we test this result, we will get the same values. So quickly testing program 3, 126. We have the same result. It's divisible by both 2 and 3. 154 is divisible by 2 but not 3. 195, it's divisible by 3 but not 2. And lastly, our neither case of 319 should be divisible by 2, is divisible by neither 2 or 3. So that worked precisely as we indicated. So let's look at example 4. So in example 4, we see the same beginning, but notice now, look at the difference in logic. And just for fun, I wanted you to see that you can test the OR condition first. And let's see how this changes the logic overall logic of the program. So we're going to say, all right, is it divisible by 2 or 3? So now, when we enter this code block, we know that one of the two conditions holds, and possibly both. So it's divisible by either, not exclusively. Okay. So now let's check. Let's begin the process of determining which one it is precisely. So here we see, all right, we check to see it's divisible by 2 but not 3. And of course, that's what we print out if that happens. Else, remember now, it's divisible by one of these two. So this is the case where we're testing first, was it the first one, but not the second? That's this block here. Now we test the other. Is it divisible by the second one, but not the first? And that's what we have here. So else, it's not divisible by 2 and 3. I'm keeping the div by 3 as the right operand of the AND function, and I'm keeping this 2 as on the left, so to improve readability. So here's what we're checking. It's not divisible by 2 and it's divisible by 3. We print out the appropriate result of this case. Now, what's the only other possibility? It's divisible by, this condition is true, so therefore, if this, you don't have a match here or here, it has to be divisible by both, logically, and again, we print out that result. Notice we come back to this else, which matches this if, and now let's think about logically what would happen. This didn't hold, so this is not true, and this is not true, so this is divisible by neither. So slightly different logic. I'm not sure which one you like best. This one has a nested if-elif-else, has a small if ladder inside the first if. So here we have nested ifs, and in the prior examples, we did not. A single if ladder in example 2, and a very small if ladder in the very coarse example 1. Let's run example 4 and see how it works. Okay, our test data 126, again, the appropriate result, divisible by 2 and 3. 154, once again, is divisible by 2, but not divisible by 3. Correct result. 195 is divisible by 3, but not divisible by 2, as expected. And finally, 319 is neither divisible by 2 or 3. So we have the expected and intended results. So let's see really what was happening in general, because it didn't really matter. Notice we have two Boolean variables here. But if we look at this generally, we're really looking at the two Boolean variables P and Q. And just so you can overlay what I'm about to say on top of our old problem, P would be divisible by 2 and Q would be divisible by 3. But in general, it doesn't matter what they are. So let's just say we have two Boolean variables p and q. What are the possible states in terms of the configurations when we jointly consider the truth and falsity of these two variables? What are the totality of possible states involved? Well, it's 4. Using the multiplication principle from mathematics, p has two states, true and false. Q potentially has 2 states, true and false. So we have 2 times 2 states total, 4. And here they are listed in a table. P and Q, P and not Q, not P and Q, and not P and not Q. And to illustrate this in a Venn diagram, now usually Venn diagrams are used for talking about sets, but when you think about set membership, an element is or isn't in a set, we can think about the Venn diagrams as well in a way in terms of the Boolean logic as well. So it's just an overlay of the kind of the set theoretic notion in terms of the logic as well. So let's look at the Venn diagram with 2 circles here. The first one is P. P is true. Here you have the circle which represents Q is true. And let's look at what it means for P. So when we look at P and not P, here we have P being true. The inside of P is shaded red. Nothing else is. And not P would be true. The outside of P is shaded red. And you would have the same thing, same similar diagram for Q, as I'm indicating now, and not Q. So let's look at one of the states, P and Q. That's the intersection. So when we say P is true and Q is true, we're saying both variables are true. And that's kind of indicated by this shaded region. So notice we have 1, 2, 3, 4 states. We have 1, 2, 3, 4 shaded regions, and I'll run through those in order. So here's another one. This is graphically what we think of when P is true, but Q is not true. Second state here. Third state, Q is true, but P is not true. The fourth state is neither P nor Q is true. So both not P and not Q, that you're out here. So neither of the two conditions is true. And really in this problem, here's what it would look like, the OR condition. So when you look at the original program and you think about coding up the logic, OR, how many different regions are in the OR? You have this region, which is P and not Q, this region in the middle, which is P and Q, and then you have the third region, which is Q and not P. And so when this, and then you have, of course, the fourth region, which is neither. So when you look at the coding here, you want to, and you think of the basic OR statement, if you just said, is P or Q true, then you can't know which of the 3 conditions it is, right? P is true only, Q is true only, or they're both true, both P and Q are true. And that's the basis of this problem. And really what we were looking at is, in a way, the exclusive OR. And that's what, in essence, we were trying to code. Now, an example that I'm not going through, there is a Python, bitwise Python function, exclusive OR, which you can use to code this example as well, which would be another example that we could consider. It's not being considered in the context of this video. Okay, so let's look at how would the code look if we had 2 Boolean variables P and Q. And notice this code parallels the code of example 4. So really this, what you're going to see is, here's how it would look if you, no matter what P or Q is, P could be divisible by 7, Q could be it's raining outside, it could be any Boolean condition. So here's how you jointly test the 4 states. You have, again, both P and Q are true, P is true and Q is not true, P is not true and Q is true, and of course with the else condition, you don't have to write it, but logically this would say it's not P and not Q. This is the classical if-elif-else ladder for those 4 states. And in a subsequent video, I will run through how this would look with P and Q and R. If you had 3 variables, you would have 2 times 2 times 2, which is 8 states. So you would have and if you wanted to know jointly exactly which of the variables p, q, and r were true, then you would need a ladder with 8 distinct branches. But that will be a topic for another video. I hope you enjoyed this video. I'm Tim Sever, and we'll see you next time.